This video covers motional EMF and induced currents. So let's say that you have a metal conducting rod with neutral charge and it is moving at a constant velocity through a uniform magnetic field. If you use the right-hand rule that we talked about in the previous video, then there is an upward force on the protons due to the magnetic field. And then there's a downward force on the electrons due to the magnetic field. So these forces are actually going to separate these two protons and electrons. So a force of magnetism is going to separate them, but we know that positives and negatives are attracted to each other, so the force of electricity is going to attract them or try to pull them together. But if these charges are not accelerating anywhere, then the forces must be equal and opposite. If the forces are equal and opposite, then we can set the electric force equal to the magnetic force, namely QE equals QVB. Again, the Q's cancel, we've seen this equation before, and we get the electric field is equal to the velocity times the magnetic field. But one of the other things we want to notice here is that there is now a potential difference between the ends of the rod. Again, remember that we talked about a positive and a negative plate having a potential difference in between them. Now we have the same thing happening here. Again, this is an induced or created, so we're going to call it EMF instead of voltage. And we can solve for this EMF by using this new equation, where this sigma is our EMF. Again, remember we used it in terms of a battery. B is magnetic field, L is the length of this rod, and V is the speed of the rod. Again, remember from our previous video that the force needed to push the rod at a constant velocity must equal the force of the magnetic field and the electric field created in the process. Again, F must be equal to I, which is the current in amps. L is the length of the rod, and B is magnetic field. So if you think about this, this is essentially the same result as two charged plates. Again, this function is like a battery. As long as we keep it moving at a constant velocity, it would induce a constant EMF. So if we connect a wire from the positive to the negative, charges are going to begin to flow as current. This is called electromagnetic induction. And this is a pressure or EMF or voltage which is created or induced, and this creates or induces a current to flow. So let's say that you place two rails made of conducting material side by side in a magnetic field, and then connect them with a wire or circuit. Then place a conducting rod across the rails. Now you can push this rod along the rails with a velocity v. So if the rod is moving, so are the charges in the rod. Again, that means we can use the right-hand rule to determine the direction of the magnetic force on the positive charges, which in this case gives us an upward force, which means that the charges are going to move along the wire in that direction. So if the charges are moving in that direction, that's the direction of our current. When the current reaches the rail, then our current starts to move along the conducting wire, shown here and here. Now, some problems might ask you for the direction of the current in the resistor. In this case, our resistor is over here on this right-hand side, so our current is actually the negative y direction at that point. So the direction of the current in the entire loop is actually clockwise. And there are three different directions shown here, so make sure that you read the problem carefully. This next part covers magnetic flux and Faraday's law. Now, the magnetic flux is defined as the flow of the magnetic field through an area of space. Again, flux is going to be represented by a sigma, which is this letter here. Again, this is flow, or magnetic flux. It's going to have units of Tesla meters squared. That means the equation must include Teslas, which are magnetic fields, and area, which is meters squared. Again, this cosine tells us that the angle between the magnetic field and area has to be parallel. Now, area is not a vector, but the normal vector, which is perpendicular to the surface, is a vector. So we're going to be using that as our area vector. The most important part here is that if a surface is involved, angles are measured with respect to the normal. We'll see an example of that next. In this case, my magnetic field and my normal vector are not parallel to each other. So we want to get them parallel. Here you have your normal vector that's going off to the left, to the right, and my magnetic field goes off in this direction. So if we want to find the parallel component, we'd have to find the x component of our magnetic field, which in this case happens to be b cosine theta. But you need to be careful because that's not always true. Now we're going to use this flux to calculate our electromagnetic induction. Electromagnetic induction is the process of creating or inducing a potential or EMF which provides the necessary electrical pressure potential to induce a current in a closed loop of conducting material. Again, we saw in our last video that a magnet moving in a loop moving in a magnetic field causes current. Well, we're going to see how changing flux also does that. So again, we have to have a changing flux. This is the most important part, changing being the operative word. Now, let's look at changing flux. Again, flux has to do with the magnetic field and the area, so there's different ways to change the flux. One way would be to change the strength of the magnetism by moving the magnet toward or away from the wire. Again, that changes B. Or you can leave the magnet stationary and move the loop away and from it, again, still changing the strength of the magnetic field at a certain point. If the magnet is a current-carrying wire, changing the amount of current will change the strength of the magnetic field. Again, still changing B. But you can also change the area. And by that, you're going to see if you turn a wire loop so that less magnetic fields are able to pass through it, then you're changing the area, therefore changing the flux. Now here is Faraday's law. This calculates the EMF, or the potential, that is induced by a changing flux in a loop of conducting material. Again, here you have your flux variable. Our sigma means EMF. And this law is written for a single loop of wire. So if you have multiple loops, you need to multiply this by the number of loops involved. Here we're asked to determine the flux. Again, it's telling us that the rectangular loop is perpendicular to the magnetic field. But that just means that my normal vector is already in the same direction as my magnetic field. So the angle between the normal and the magnetic field is 0. So we don't even have to worry about the cosine here. So plugging in all my numbers, I get 0.0672 Tesla meter squared. Here is the continuation of the problem. Here, the magnetic field is being moved to a very far distant away, a very distant point. That means that my magnetic field is essentially 0. So if I want to solve for my induced EMF, my flux when my magnetic field is equal to 0 would be 0. My magnetic flux at the beginning was 0.067, and the time it takes for this to happen is 5 seconds. So I get 0.0134 as my potential, or induced EMF. In our previous videos, we only said that we were moving a rod into the field. Now we're going to move an entire loop of conducting material in and out of the field. Now I want you to think of the loop as full of positive charges. So if the loop moves to the right, then so do the charges. Right now the loop is not in the field, so nothing's happening. Using your right-hand rule, when the loop enters the field, now we have a force upwards that causes a current to flow in the direction of these blue arrows. So right now, our charges are flowing in the counterclockwise direction. The interesting thing is that when this loop is entirely in the magnetic field, that force, that upward force, is acting on all of the positive charges. So there's actually no current flowing at all. But when our loop of wire moves out of the magnetic field, then you have, again, using your right-hand rule, see that the charges start to move again, and we now have a current, but now it's in the clockwise direction. Again, make sure that you practice the right-hand rule in these examples. So here's a summary of what's happening. Now, again, this is situational. It does depend on the direction of the magnetic field. If the magnetic field were flipped, everything would be in the opposite direction. Now, we've seen the first equation before, this one. But now we introduced this one. Again, the left one is definitely easier, and it helps if you understand where it comes from. So let's say that our area is increasing. That means we're moving it into the wire. as area increases, again, you're going to see an increase in potential. Here, if my width increases, that's still an increase in potential. But now we have width over time, where length stays constant. So width over time is distance over time, meaning we can replace that piece with velocity. Let's go ahead and summarize it using only variables. Here we have a loop of wire of length L and a resistance R. It is moving at a speed v through a magnetic field of magnitude B. Answer this question in terms of B, L, V, and R. Again, our EMF is just going to be B, L, V. Our current, which is I, is equal to our EMF over R. So we can actually leave it in terms of B, L, V over R. Now these are important so that you can do the multiple choice a lot faster. Here we're asked for rate that energy is generated, which is just power. We said before that power is equal to current times voltage. In this case, current is BLV over R, what we saw in the previous example. Our voltage, or EMF, is going to be BLV. So if we simplify this, this is B squared L squared V squared over R. And then finally, we're asked to determine the force needed to keep the loop moving at a constant velocity. Again, we said that this force is going to be equal to our magnetic field, which in this case is ILB sine theta, where theta is equal to 90. Our current is from before, BLV over R. Our B and L and B are variables that we can use in our final equation. Again, we get B squared L squared V over R equals F. The force needed to be applied in order to move at a constant speed. And finally, we have Lenz's law that states that the magnetic field of the current carrying wire, which in this case is a red loop, is going to oppose the change in the magnetic field that created the current in the wire. Again, go ahead and write this part down and we'll see examples of what it means. So down here, we have this red wire that's moving into the blue magnetic field. As this red wire goes into the magnetic field, the amount of X's is going to increase. So again, Lenz's law says the current created in the red wire has to flow in the direction that opposes the change of the blue magnetic field that takes place inside the red loop. So let's say we have this red wire going to this magnetic field. We've already seen that we're going to have a current that goes in this direction, okay, if the velocity is moving to the right. That means if you use your other right-hand rule, that my magnetic field is going to be going out of the page. So we're going to represent this by red dots. So the magnetic field created by the red wire is shown by the red dots. So again, my magnetic field by the wire is going to be in the positive Z direction, whereas the magnetic field that's already there is in the negative Z direction. Again, as it's going into the magnetic field, it wants to oppose the magnetic field that's happening on the inside. Now, what if the wire is pulled back out? Well, again, the previous right-hand rule that we saw in this problem, in this video, tells us that our direction of the current is now going to change because the force is going to push the charges in the opposite direction. Well, that means if you were to use your other right-hand rule that tells us that my thumb goes in the direction of this current, I'm going to have a magnetic field that goes into the page here. Okay, now represented by X's. So my magnetic field by the current carrying wire is now in the negative Z direction. My magnetic field by the blue piece is still in the negative Z direction. But the reason that they're in the negative Z direction is because this is going down. So to oppose that change, we need to increase our magnetic fields in that direction. Over here at the top, as my magnetic field was increasing, we're opposing that change, so we're canceling it out. So looking at this example, we can use our right-hand rule, which tells us that our magnetic field is going to be coming out of the page on the left side and into the page on the right side. Now, if we have increasing current, that means these blue dots are going to start increasing, just to show that the magnitude of the magnetic field at that point is also increasing. So if we had a wire over here, that increase in magnetic flux would actually produce a current in this wire, but this wire is actually going to create red X's, meaning our magnetic field is going to be going into the page at that point. So in order for that to happen, my current has to be flowing in the clockwise direction. Again, using the right-hand rule. Here we still have a current that's going upwards, so I'm still going to have a current that comes out of the page on the left and into the page on the right. If I have a wire here, this decreasing current is going to decrease the amount of dots inside of my wire. So my wire is actually going to produce a current that counteracts that, meaning it's going to be creating red dots as well, meaning the magnetic field is going into the page. In order for that to happen, out of the page. In order for that to happen, the current has to be going in the opposite direction, the counterclockwise direction here. Again, using the right-hand rule.